Yeah, most people think that ceramics are brittle. Drop your coffee cup on the floor and you have a very large chance that it's going to break into a million pieces. But in reality, we're engineering ceramics these days. We can engineer structural ceramics that you could drop on the floor as many times as you wanted to, and it would have very little chance of failure.
So our signature area is called Enabling Materials for Extreme Environments, and this is really an outgrowth of research that Professor Greg Hilmes and I have been doing for about 15 years. So we started with funding from the U.S. Air Force to look at materials for hypersonic aviation. The future hypersonic vehicles that the Air Force and others would like to fly are going to have sharper leading edges, and the idea here is that this would fly more like a conventional aircraft. The engineering trade-off for that maneuverability is that the temperatures right at the leading edge could be 2,000 degrees Celsius or higher. Zirconium diboride and some other carbides and borides are really the only materials that have melting temperatures high enough to withstand this environment. And our signature area is really looking to expand that into other applications.
Normally when you break a ceramic, you might break it in bending. So you load that material up in a flexure fixture. You can watch the material maybe start to bend a little bit, but ultimately you're building up a lot of energy and that material explodes. Now if you develop a material based on a composite technology, like the co-extrusion process that we're doing in our labs, you can develop a material that is really truly engineered. It has the same basic material as the monolithic ceramic that fails catastrophically, but when a crack runs in this material, we actually have another phase engineered into the architecture that mitigates crack damage and not fail catastrophically.
We've really built up a pretty unusual combination of equipment and research expertise in this area. I would say unique in the U.S. in terms of the facilities that we have at a university.
Another big problem in extreme environment applications for ceramics is their poor resistance to thermal shock. A good example that folks might know out there in the real world is if I take a hot glass out of a dishwasher and put cold water in it, it might just break in my hand. In the ceramic world, if I'm going to use something as a rocket nozzle, now that material's got to be able to withstand maybe room temperature a little lower to maybe as high as 2,000 or 3,000 degrees Celsius. Now we can take a material that maybe could only withstand a 300 or 400 degrees Celsius instantaneous change in temperature to now it can withstand maybe 1,500 degrees C instantaneous change in temperature.
Concentrated solar power is one of the other applications that we've targeted. An array of mirrors is used to focus the sun's energy into a small area where it's collected and converted from solar energy into thermal energy that would be stored in some kind of a medium like a molten salt. The problem is that, again, you create such an extreme temperature and extreme heat flux that very few materials can withstand that environment.
There's generally three classifications of materials: metals or metallic conductors, semiconductors, and then ceramics, which are mostly known from an electrical perspective as insulators. But there are ceramics that actually do have some electrical conducting capability, so they're bonded in a number of different ways. One of the materials that we're working on for our extreme environment applications is zirconium diboride, and we're currently doing plasma arc welding of zirconium diboride. So we're basically creating an electric arc with a gas flowing through an electrode that, of course, we're not consuming, and we're just creating a plasma between the tip and the ceramic and creating a molten pool of zirconium diboride and plus other additives. We think there's even some potential to take this technology to welding insulating ceramics. What if I could just come back and take that crack in the material, puzzle piece the part back together and just weld it back and have it be in the pristine condition that it was originally. So the field of ceramic composites is a booming area right now. There's companies out there that are now replacing metals with ceramic composites because they can withstand higher temperatures and they have the toughness that a metal does.